Hey, welcome back everyone, it's Kevin again, and in our last video I took you to my bookshelf and I explained how this bookshelf could be used as a metaphor for the OSI model. We said that the OSI model consisted of 7 different layers. Let's check out those layers as a reminder. We gave you a memory aid. We said starting at the bottom we could remember the acrostic of "Please do not throw sausage pizza away." The P in please reminding us of the P in physical, and the D in don't reminding us of the D in data link, and so on. These are the different layers of the OSI model, and the reason we brought the bookshelf into the discussion was we wanted you to think of each of these layers as a way of organizing network components. Just like I had my bookshelf organized into different types of books, we're going to organize different types of protocols, different types of standards into the different layers of the OSI model. And over the next few videos, we want to dissect this model and start taking a look at some of the different layers. In this video, we're going to take a look at layer 1, the physical layer. Before we do that though, there's a bit of terminology we need to get straight. When we talk about data at different layers of the OSI model, that data has different names. These different names are different protocol data units, different PDUs. When we have ones and zeros, binary ones and zeros down at layer 1, those are bits. At the physical layer, we have bits as our protocol data unit. At the data link layer, we have frames. And you'll notice that packets show up at more than one layer. Packets technically is a layer 3 protocol data unit, but the term packet has come to be used as more of a generic term referring to protocol data units at layer 2 or 3 or 4. So that's why we're showing you that here on screen. But technically a packet is a layer 3 protocol data unit. At layer 2 it's a frame, at layer 3 it's a packet, or a datagram at layer 3, that's another valid name. And at the transport layer, it's a segment. Here's another memory aid for you. Starting at the top down, we could remember the acrostic, "Some people fear birthdays." Some people fear birthdays to remind us of segment, packet, frames, bits. Or going from the bottom up, we could remember bacon frying produces salivation. That's one of my favorites. So just keep in mind, we've got these different names for data at different layers of the OSI stack, and our focus in this video is going to be on layer 1, the physical layer. Oftentimes when we think of the physical layer, we think of things like the wire, the copper, or the fiber. Or we think that, oh, that's a hub. A hub lives at the physical layer, and that's true. But the physical layer actually has more jobs than a lot of people realize. I really want to get in depth in this OSI discussion over this series of videos because I really think it's being de-emphasized in a lot of network curriculum today, and I want to make sure that you guys have a really solid understanding of it. So let's take a close look at the physical layer. Notice that the physical layer specifies how bits, how ones and zeros are represented on the medium. Now let's ask ourselves, how do we represent a binary 1 or a 0? If it's a copper wire, we might represent a binary 1 with the presence of voltage, a certain voltage level. A binary 0 could be represented by the absence of voltage. If we're representing binary bits over a fiber optic cable, it might be the presence or the absence of photons, the presence or the absence of light. And what I've just described is current state modulation. It looks like this. With current state modulation, the presence of voltage, it might be positive 5 volts or negative 5 volts, and this can vary depending on your standard, but the presence of voltage, positive or negative, could indicate a binary 1. The absence of voltage, 0 volts on the wire, could represent a binary 0. And the approach that's being used in this illustration is something called alternate mark inversion, or AMI. The idea with alternate mark inversion is this. We would like to have an average of 0 volts on the wire. That's a desirable electrical characteristic to have an average of 0 volts on the wire. And the way we have 0 volts on the wire on average is when we send one binary 1, it's a positive voltage. When we send the next one, it's a negative, and the next one's the positive, and the next one's the negative, and so on and so on. And as an analogy, you can think of it this way. If I take one of my hands and I stick it in a bucket of ice cold freezing water, and I take my other hand and I stick it in a pan of boiling hot water, On average, I'm going to be comfortable. Okay, it doesn't work like that way for humans, but that is the way it works with current state modulation. But this is not the only way to represent binary ones and zeros. In addition to the current state modulation, as another example, we have state transition modulation. Here, notice that we get a binary 1 only when there is a change in state. When we go from 0 volts to a positive voltage, that's a change in state. That represents a binary 1. So even though we might have a positive voltage on the wire, if we have a positive voltage that is maintained across a couple of timing intervals, that's still going to be a binary 0 with state transition modulation because we didn't transition. We stayed at a positive voltage, which means that represented a binary 0. Just a couple of examples of how binary 1s and 0s could be represented on the wire. Let's remind ourselves of a few other things that the physical layer can do for us. Wiring standards for connectors and your jacks. For example, if you have an RJ45 connector and you're setting this up for Ethernet, you're going to be using pins 1, 2, 3, and 6 to carry your Ethernet signaling. There's a standard for how RJ45 connectors are wired up. There's the TIA, the TIA-EIA 568B standard. That's a standard that says how we should wire up an RJ45 connector for a 100 base TX Ethernet network, as an example. The physical topology that we have, that's a physical layer component. Here we're talking about, do we have a bus topology? Do we have a ring topology? Do we have a star topology? Synchronizing bits. If we have two different devices communicating with one another, in order for those two devices to successfully communicate, they need to agree when one bit stops and another bit starts. They need some way to synchronize their bits, and there are two basic approaches to this. There is asynchronous and synchronous synchronization. With asynchronous synchronization, the sender tells the receiver that it's about to start transmitting. It sends a start bit. And when the receiver sees that start bit, the receiver starts its own internal clock to measure the subsequent bits that it receives. And then after the sender starts sending that data, it can then send a stop bit to indicate that it finished. That's asynchronous. What about synchronous? The synchronous approach to synchronization uses internal clocks of both the sender and the receiver. The sender and the receiver have to agree when bits start and stop. And a common approach is to have the internal clocks of the sender and the receiver reference an external clock, maybe a service provider's clock, and that way they can both agree on when one bit starts and another bit stops. It reminds me of the saying that a man with one watch always knows what time it is. A man with two watches is never quite sure. You want to make sure that you have one watch that the sender and the receiver agree on the clock. Bandwidth usage, that's a physical layer component. And here we're talking about the distinction between broadband and baseband. Broadband is a lot like your cable TV, where you have different frequency ranges, different channels essentially, that carry different transmissions. You can tune in to different channels by tuning in, by listening to different frequency ranges. That's broadband. One example of a broadband technology is frequency division multiplexing. That's what's used by a lot of cable modems. The cable modem is going to use certain frequency ranges on the cable coming into a home. One frequency range is going to be used to send data. Another frequency range is going to be used to receive data. Another bandwidth usage approach is baseband. With baseband, all of the available frequencies on the transmission medium are used to carry a single conversation. And finally, we have the multiplexing strategy. How do we carry simultaneous sessions on a single cable, as an example? Well, cable TV is one example. We could have different channels, and we could tune into different frequency ranges to tune into those different channels. And some of the common multiplexing strategies out there include TDM, time division multiplexing, statistical TDM, and frequency division multiplexing. Let's consider each one of these. With time division multiplexing, the different communication flows that are sharing a medium, they literally take turns. There are different time slots that are defined, and when it's time slot number 1, channel number 1 gets to talk, and when it's time slot number 2, channel number 2 gets to talk. To paraphrase Whitney Houston, each channel gets one moment in time. And you might look at that and say, well, that's great, but what if there are some channels that don't need their time slot right now? They have nothing to say, while other channels are just chomping at the bit to be able to send on the network. Well, there's an approach to make this better. We could use statistical time division multiplexing. With statistical time division multiplexing, time slots are dynamically assigned on an as-needed basis. And finally, frequency division multiplexing. That's going to divide the available frequencies in a medium into different channels, like the cable modem we were talking about earlier. So again, three big ways of doing multiplexing include time division multiplexing, statistical time division multiplexing, and frequency division multiplexing. And if you're looking at physical pieces of a network and saying, I wonder what fits into the physical layer of the OSI model, well, remember, your connectors are defined here. Your wiring is defined here. And a device that's become sort of a legacy device these days is a hub. A hub is sometimes called a bit splitter because it takes bits in on one port and it regenerates those bits going out of other ports. It doesn't make any intelligent forwarding decisions, it just spits bits out all the other ports other than the port that the bits were received on. And a hub is a physical layer network component. Well, I certainly hope that this video has given you a deeper appreciation for the physical layer of the OSI model. We'll see you back next time for the next video as we continue our climb up this OSI ladder.